Hi, it's time for another math easy solution to discuss further into the laboratory project on Taylor polynomials, and I'll look at question 6, which would look at an example on Taylor polynomials. And if you haven't already, make sure to watch my earlier videos on questions 1 through 5. The links will be in the description below, or you can just go to my channel and search Taylor polynomials. And just to quickly recap, in the earlier videos I went over a quick recap on linear approximation, and then I went over a quadratic approximation with with these stipulations where I set the approximation equal to the function as well as all its derivatives all equal at a x equals a value there, which is basically the area that, or the interval that we want to approximate, so near that value x equals to a. And then I solved for a quadratic approximation, or a power of 2 as the biggest polynomial, or in other words a second degree polynomial. I showed that it's better than a linear approximation. Then I went over some accuracy, as well as then in question 3 I went over a different format for the quadratic function, writing it like this to set up for the Taylor polynomials one. Going further, did another example. Then in the last video I went over the nth degree Taylor polynomial and basically extended beyond just the quadratic and beyond just the linears over there. Power of 1 is linear, power of 2 is a quadratic. Then you can go to the cubic, you can go all the way to n over there. Then when you solve for the constants, when you set all the derivatives equal to each other at x equals to a, that is again the point we want to approximate nearby. Then I showed that we get a pattern for the constants going to be equal to the derivative at that value a divided by k factorial. And that's associated with whatever the constant is over there. Then the resulting polynomial is, we get this, and this is what's called the nth degree Taylor polynomial of f centered at a. In other words, we have Tn of x equals fa plus f prime of a times x minus a, and then plus the second derivative divided by 2 factorial, then x minus a squared. Then you keep adding this and keep going on till the nth derivative of a over there, of f at a divided by n factorial, and then times by x minus a power of n, and so on. And again, this approximates the function f and centered at a or near that value x equals a. So now let's look at question 6. So question 6 states, find the 8th degree, so we're looking at 8th degree Taylor polynomial centered at a equals 0 for the function f of x equals to cosine of x. And then it also states in this example, graph the function f together with the Taylor polynomials t2, t4, t6, and t8 in the viewing rectangle -5 to 5 by -1.4 to 1.4. This is just the x interval, this is the y interval, and comment on how well they approximate the function f. So here, first of all, we're asked to find the 8th degree Taylor polynomial, and in that, these t2, the second degree, and the 4th and the 6th degree are all encompassed by the 8th one. This one includes all of them, as I showed above here. The nth one includes the 1, 2, 3 over here. So we could just solve for the 8th one, then we've automatically solved for the 2, 4, and 6. So let's go ahead and start solving this. First of all, let's write our Taylor polynomial, just a generic one over there. So we know Tn of x is equal to f of a, and then plus f prime of a, x minus a, like that. And then we have a f double prime of a divided by 2 factorial, then we have x minus a, and then we have it squared, plus keeps going on and on. And then finally we get all the way up to here, f. This is going to be the power, the nth derivative, put it like that, bracket, and then n of a, and then this is going to be n factorial, then we have x minus a, to the power of n, like that. So now that we have that, now let's go and try to solve for the derivative. So let's write find derivatives. To find derivatives all the way. I'll just write find derivatives f and then put a 0 there for just the generic one. This is going to be at a. This is the 0. You can consider that Then we have the second derivative. I'll put a 1 in there. This one's the same thing as that. And then we go all the way till f of 8 right here. And then this is where, and I'll just write where n equals to 8 is what we want, and x equals to, or I'll just write at x equals to our a value, which equals to 0. So we're asked to do it centered about 0. So let's go ahead and do this. So the first derivative, f, just the 0th derivative is just a function f of x. This equals to just our function cos of x. That's just cos of x. And then the derivative, f prime of x, is going to equal to, this one, recall, this is just going to be negative sine of x. Now we take the derivative again of this, f double prime of x. This equals to, well, that's just going to be negative cosine of x. Like that. Negative cosine of x. And then likewise for the third one, 1, 2, 3 of x, this equals to the derivative. This gets flipped, it's going to be negative of a negative sine of x, so it becomes positive sine of x. Like that. And then the fourth derivative, like this, equals to, this is sine of x, it's going to be cos of x. And now notice over here, this just equals to our f of x. Now we're back to square one. Like that, that just equals to that. So then this pattern just repeats itself. Pattern repeats, I'll write it like that. Yeah, so it repeats itself. As you can see, this is the fourth one, so the fifth is going to be negative sine, the sixth will be negative cos, the seventh will be sine, and then the eighth will just be cos of x. And then we just keep going. I'll just write the eighth one right here of x equals to cos of x equals to f of x. It's all equal. So now let's plug in our values at x equals to a. So we have over here f of 0 is equal to, well, cos of 0. Recall that cos of 0 is just, well, 1. So this is just 1. And then we have the first derivative. It's going to be negative sine. So then the f prime of 0, this equals to negative sine 0. Let's put this inside here. Cos 0, this equals to 1. And this one's going to be negative sine 0, which equals to, well, 0. Recall is just 0. Like that. And then likewise over here, negative, and then 1. So f double prime of 0 equals to negative 1. And then we have over here sine, that's just going to be 0 again. f1, 2, 3, 0 equals to 0, like that. And then this one over here, we just put that inside, that's just going to be, well, f of 4, 0 equals to, yeah, this one is just plug that in, that's just a 1. So then notice how we've repeated itself. So we have 1, 0, negative 1, 0, and then 1, and then likewise the pattern will repeat. I'll just put 0 in here. The fifth one, because remember the fifth one, everything starts repeating. So the fifth is going to be, we go from the 1 here, and this I'll just write here as this equals to f of 0, like that. So then this repeats, this will be a 0. And then the sixth one, let's put the sixth one here. Yeah, the sixth one of 0 equals to, goes 1, 0, and then negative 1, like that. And then the seventh, just by the pattern, equals to, of 0 equals to 0. And then the last one, this one's over here, f of 8 of 0 equals to, well, just 1. Yeah, so thus what we end up having is, so thus, for n equals to 8 and a equals to 0, what we end up having is t8 of x is equal to, I'll just write this down, f of 0, like this, plus f prime of 0, and then we have x minus 0. Oh yeah, a is just 0, so we just have x like this. Because we're doing x minus a, x minus 0 is just that. And then we have the second one, f double prime of 0, divided by 2 factorial, then we have x squared, plus 1, 2, 3, and then 0, x 3, divided by 3 factorial over there. And then we can keep going here, add the fourth one here, f of 4, 0, then 4 factorial, x to the 4, and then we can keep going. Let's do the fifth one, f of 5 derivative. 0, and then we have x to the 5 divided by 5 factorial plus f of 6. Let's keep going here. 0, x to the 6 divided by 6 factorial. Then keep going. Let's do the 7th derivative of 0, x 7 divided by 7 factorial. And then finally f of 8th derivative of f at 0, x 8 divided by 8 factorial. And now we can start plugging in our values. So t8 of x equals 2. So let's just scroll up. So f of 0 is equal to 1. So we have 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So notice the pattern. So this is going to be f of 0 is equal to, that is just 1. Then we have 0. So just put the whole thing vanishes. Then we have this one here is going to be negative 1. So we have negative 1 over 2 factorial x squared. Then we have over here 0 plus 0. Then we have over here the fourth one is going to be a positive 1. So plus 1 over 4 factorial x to the 4. And then we have over here another 0. Yeah, this is the fifth one all the way over across here. I'll just go over here. Plus 0. Yeah, so look at the pattern. So we have 1, 0, negative 1, 0, 1, then 0, then we have to have a negative 1 over here, negative, and then just put an x6 over 6 factorial. And then we have another 0 over there. And then finally plus 1 x over x power of 8 divided by 8 factorial. So we can simplify this further, just get rid of the 1s, write it a bit neater. So we have t8 of x. So the 8th degree Taylor polynomial is equal to 1 minus x squared over 2 factorial plus, here's going to be x to the 4. Yeah, let's put x to the 4 over 4 factorial like this, and then we just add all the even ones, all the other zeros, the odds vanish over there. Yeah, this is x to the 6, and then we have 6 factorial plus finally over there x to the 8 factorial. Yeah, so thus this is our 8th degree polynomial, and this should approximate, or we're looking to approximate cosine of x, and this is again near x equals to a. Yeah, move that over here, near x equals to a, which equals to 0. So I'll just circle this whole thing, and there is our answer, and that's supposed to approximate our function f of x over there. Yeah, so that's our 8th degree Taylor polynomial, but also we can find the other ones are all encompassed inside. So also t2 of x, that just equals to, well, this is the 0th one, and then remember the other one is the 0. This is the 0th term, the first term, second term, and that's just the quadratic there. So this is just the quadratic approximation. That's just the first part over there, 1 minus x squared over 2 factorial. And then to solve for the t4 of x, this equals to, well, we just go one further over there. So you have 1 minus x squared 2 factorial, and we just keep adding to it, plus x to the 4 over 4 factorial. Finally, the 6th one over here of x equals to 1 minus x squared over 2 factorial plus x to the 4 factorial. The next one is going to be subtracted by x to the power of 6 factorial, as is over there. So basically each one we add, each iteration we just add another term that gets bigger and bigger, not in fact more and more accurate, as I'll show. Yeah, so now let's graph those approximations, the 2nd degree, 4th degree, 6th degree, and 8th degree, as well as f of x equals cos of x. So here I've done that using the Desmos graphing calculator. The black one is the f of x over here. That's our cos of x. And here is centered about at x equals to 0. So this is our a equals to 0 over there, or x equals to a equals to 0. So notice the approximation. They're all close over here, but as you get further and further, this purple one, that is t of 8. So I'll write t8. And then the next closest one's over here, the red. And the red one is t6. And then the next closest is the green. Notice the Taylor's off beforehand. over there as it gets further and further. This is our t of 6. I mean, a t of 4 is the green, and then as you see, the blue one is over there, and it's just pretty much a parabola going downwards. This is our t2 like that. So yeah, so notice how each Taylor approximation closely approximates near x equals a, which equals 0, but each successive iteration is shown to better approximate f of x equals cos of x further and further away from the x equals a equals 0 interval or point over there than the previous iteration. So yeah, t2 is just approximating closer to this, and this one Taylor's off beforehand, and then it gets further and further, it's closer over there, and then the t8 is the one that goes back up there, and obviously when you increase it to go to the t10, t12, all the way to 100 and so on, you get better and better approximations. You just want to click through here, just go and play around with the Desmos calculator because it's quite amazing. Let's just see it at bigger scale. It's just, okay, it's over here at projector mode. Move this out. So yeah, there's some cool stuff over there. Yeah, so the green one, yeah, the green one went back up over there. Whoops. Let's see some other cool stuff here. So as you can see here, this is the T8, and that is again the purple one, T8. And there is the red going straight down, T4 going up, and this one going straight down here. And then obviously when you keep increasing them, it's going to go back loop, and keep looping around. So yeah, go play around with it. Go find the T10, T12, and let me know what you come up with. This is some pretty amazing stuff. Here's a pretty amazing calculator too. Anyways, that is all for today. Hopefully you followed along. Hopefully you enjoyed this entire series on the laboratory project on Taylor Polynomials. Let me know what you think. Hopefully it helped. And yeah, make sure to watch my earlier parts. Some very insightful stuff in here. Anyways, that's all for today. Thanks for watching. Like always, you can download these exact notes in the link in the description below, as well as viewing these notes on Steam and in article format. Make sure to follow me at MES, and also make sure to check out my math and science forums. And yeah, post any cool math or science related stuff you find. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.